Welcome back, math lovers. Today I'm here to meet you with a very interesting concept of calculus. So most of them are very sure about what is this first differentiation, because we have even posted some videos about the role of first differentiation, what it does to the function or the curve. But we must also be aware of what is this second differential, right? So what is first differential? Again, it is about the slope of tangents drawn at each point of that curve. Okay, so let's get into detail. Let me take a simple cubic equation for better understanding. X cube minus 6x square plus 11x minus 6. So you can see this the graph of this cubic equation. It was increasing continuously until this particular point. Okay, and it has its roots at 1, 2 as well as 3. So the roots of this cubic were 1, 2 and 3. And this graph was continuously increasing from minus infinity till this particular point, and then it was decreasing till this particular point, and then it started increasing again. So there are three intervals I could spot out. So one is your x values moving from minus infinity till that particular point where you are reaching a high point, which is like coming as 1.42265 in x value. Until that, what you can notice is the graph. So whenever you read a graph, you have to read it from left to right. So in this graph, I would say the graph was increasing. And from that particular point onwards, 1.42265, the value in x, until the next particular point. So where is the next particular point? Till here, which is 2.57735. It's an approximate value. So until there, you can see the nature of the graphing kept going down. And after that 2.57735 till the positive infinity, the graph is continuously moving upward. So you can say here the graph is increasing and here the graph is decreasing, and here again the graph is increasing. Correct. So now this is being validated with the help of our first differential. Let's see what's happening. So the first differentiation of this cubic function is going to be 3x square minus 12x plus 11. So the blue graph denotes the same. So now we can understand where exactly the blue graph is hitting a minimum point. So like this blue graph is actually the value of your first differential. So I would say the blue graph is indicating our value of f dash of x. And this f dash of x is becoming 0 at 2 points. Okay, this f dash of x is becoming 0 at 2 points, which is exactly inclined to the same points of this interval, right? So as we are marking these points, 1.42265 and the other point 2.57735, these 2 points are marking as the specific points at which your f dash of x became 0, correct? So at x being 1.42265 and at x being 2.57735, exactly your f dash of x had become 0. Okay. The reason of this is the first differential test is actually helping us to understand where you are reaching your maximum value or minimum value. It's like also called as local maximum or local minimum, because in this small interval, right, from minus infinity till this particular point, can't I say this was the local maximum, because that was the highest value that this curve has faced, correct? And after that, you can see the curve has actually faced much more higher values. Now let's talk about what this second differential is going to do. So second differential is going to help me. So you can look at the nature of this graph, this first differential graph. I'm going to show you the values as such. Can you see these people? What's happening to the values? As the x value keeps increasing, what's happening to the slope value? F dash of x is going to give you slope, isn't it? What's happening to f dash of x value? The slope value is continuously decreasing. It was continuously decreasing until this particular point. Until this particular point, x being 2, it was continuously, your slope was decreasing. After that particular point, what happened to your graph? The graph values is slowly starting to increase, correct? So your values of slope is continuously increasing. So there was only two set of data with respect to this particular f dash of x information. So here I had shown you, whatever I had shown you was about f of x information. Whatever I had written here was nothing but about f of x, where my f of x is increasing, decreasing, that. But now I'm talking about f dash of x. My f dash of x from minus infinity till x reaches 2, the slope was continuously decreasing. The slope was continuously decreasing. And right away from 2 towards the positive infinity values for x, the slope started to increase. So the value 2 is marking a very specific information like about the slope nature, right? It's about the slope nature. The slope was decreasing till then, and then it started increasing. Okay. So as you can understand, what does slope decreasing mean? It's about the tangent angles. So what's happening to the tangent angles slowly? So I will also draw certain tangents for a better understanding. So this be a tangent here. I'll try to focus with the line. Let's say I'm drawing a tangent at this point. You can see the angle here. And at this point, let me draw a tangent. So you can see the angle much more reduced. The angle gets much more reduced. So you slowly start to understand that tangent is having much smaller acute angles till I reach this particular point. So at this particular point, there is something happening. So after this particular point, what's happening? So this is what is our f dash of x information. Let's talk about the f double dash of x curve now. So the differentiation of the first differential, this is going to give me 6x minus 12 people. Okay, 6x minus 12. So you can clearly understand the second differential is like a continuously increasing thing, isn't it? The second differential shows a continuous increase because it's a linear thing. And exactly at the point 2, which your f dash of x indicated, exactly at that particular point 2, your f double dash of x became 0. F double dash of x became 0 at x equal to 2. Okay. So that indicates the point where that particular point, f double dash of x being 0, is called as inflection point, people. It's called as inflection point. So many people confuse about what this inflection point is. I'll keep it in short. So inflection point is a point where your curve is turning upward or downward based on the slope nature. So can't you see this? I'm redrawing the curve again on the same path. So this curve, whichever I'm drawing, was like this. Okay. After which the curve started becoming like this. So in short, if I draw the miniature of the same, it's like this followed by like this. So this path until this is called concave down, curve facing downward, and this is called concave up. So where your tangent will be placed for a concave down curve and where will your tangent be placed for a concave up curve? That is only going to decide. Okay. For a concave up curve, the tangents drawn will be below the curve. For a concave up curve, your tangents will lie below the curve. Tangents will lie below the curve. And your concave down curve, your tangents will lie above the curve. Your tangents will lie above the curve. So what exactly is that inflection point then? So that's the point where your tangent is starting to change its nature from above the curve to below the curve or below the curve to above the curve. So this transition is marked only by the inflection point. Hope you understood it. I'll even draw the tangent equation at that point x equal to 2. We know how to write a tangent equation. So I'm talking about the point x equal to 2. At x equal to 2, I want to write the tangent equation. So at x equal to 2 means y value is 0. That also you can know. We'll use a 1-point slope form, y minus y1 equal to slope times x minus x1. Okay. So x1 value being 2 and y1 value being 0, I need the slope. Okay. Slope is nothing but this curve, 3x square minus 12x plus 11 curve. I am going to substitute x equal to 2 in that. Let's see what happens in this if I substitute x equal to 2. I'll be getting 3 into 2 square minus 12 into 2 plus 11. So this becomes 12. 12 plus 11, 23. Okay, 23 minus 24. So we're getting it to be negative minus 1. So you are getting y equal to minus x plus 2. So this will be the equation of tangent at the point x equal to 2. So y equal to minus x plus 2. Okay, hope you can see that. I'll even remove all the other curves to get a better clarity for us. I'm removing the second differential curve. I'm removing even the slope curve. Okay. Are you able to see, people? This tangent is above this uh, particular curve, the concave down curve, and it's at the same time it's seemingly below this concave up curve. So that's why this particular point is termed as inflection point. So this inflection point, I will tell you the application also in short. So we are all uncertain of our futures, right? So this inflection is a very important terminology, I should say. Suppose there is a specific epidemic spread out and there is a curve like this, okay, and there is a curve like this. So maybe like both of the curve at the same point, I mean at the same time interval, we would all understand they are at the same value as such. But after which, what is going to happen? That is only future, right? So this inflection will help us to understand whether after this it's going to fall down or is it going to go above. Will the disease spread increase just like our COVID, or will the disease spread fall down? So this critical information which we need is being presented in the simplest form of a graph, which is called as inflection point. Hope you like this video. Like, share and subscribe. Thank you.